Hi everybody, welcome back to a good old energy review. Welcome back to Monday. And yeah, we got some good stuff. Today is a quick little review about energy. We're going to try to do the whole unit in terms of like reviewing content in a day, and then the rest of the week I'll just be kind of practicing energy because it's super important, it's super good. Yeah, it's just a great topic. It's a good one to ask questions about. And if we can understand energy, we can pretty much understand everything in this unit. Or everything in the whole course. You can approach anything with energy, which is great. So what we're looking at today is trying to construct an explanation, trying to explain what we see based on energy transformations. I'll get to that in a second. So what we're going to do is we're going to watch this cool Rube Goldberg video, which will kind of be like our guiding phenomena. So talking about like, hey, energy transformation shows up during this Rube Goldberg, which is a cool little thing that we'll look at in a second. So how does this work? How can we explain what we're seeing based on energy transfer? Then I'll give you a quick little lecture about it, and then you'll really have two things for the next 2 days, for Monday and Tuesday. A quick little Google form about this Rube Goldberg, and then some practice with energy. So you'll be able to split that up however you want. These energy questions are a little bit more multiple choice based, not free response based. Wednesday and Thursday will be free response. Yeah, so without any further ado, let's get into it. So Rube Goldberg machines, you guys have probably heard of them. It's just a cool way to perform a task in an overly complicated way. So I've been seeing a few of people just bored in their house bored of them making Rube Goldberg machines, and they've been cool. They've been like kind of creative. This one's the one that I'll show you is my favorite one that I've seen. And yeah, so mainly they run on physics, this idea of conservation of energy and conservation of momentum. Today we're going to focus on the conservation of energy portion. And we're going to be able to identify later on, kind of our goal is identify moments where we see energy transfer in this video and talk about what kind of energy we see, what kind of energy transfer are we noticing. So I'll kind of show you guys this video. I'll be down at the bottom. And let's see here. Let's see how they kind of give it a little push. Let me restart it. Ugh. Give it a little push, and then yeah, it restarted on its own. This is just kind of cool. I like that they kind of memeing on the self-isolation. Not really memeing on it. They're taking it seriously, just you know, doing it with toilet paper because that was the thing back in the day. I like the idea of the pink toilet paper. I don't think I've ever seen it in real life. I don't know where they bought this from, but it's kind of cool. It's kind of festive, I guess. I don't know. Yay, and then they get some hand sanitizer. And I think they, I like how the whole thing is a continuous shot, and then I think he didn't stick his hand out in time or something, so yeah, I don't think anything squirts out of there. Oh, a little bit does, yeah. Alright, cool. But nevertheless, we want to kind of talk about the different modes of energy transformation that we see in there, remind ourselves about energy transfer and all that good stuff. So the first thing we have to do when we talk about energy transfer, the main thing, the most important thing, is we have to define a system. So the College Board defines a system as an object or collection of objects. The objects are treated as having no internal structure. So they're just saying, hey, it's these objects. When I think about a system, the way that I define it, the way that I put it, is a little bit simpler than that. It's just the objects that we care about. So it's us coming into a situation and saying, what do I care about? What objects am I looking at here? When I'm thinking about this energy transfer, where is energy being transferred? Between what objects? Like if we defined everything that happened in that Rube Goldberg machine, all the objects in that room is the system, we'd say, hey, energy was transferred within that system. If we defined all of the objects in that room and then my water bottle as part of the system, that'd be weird to include my water bottle in the system. We don't care about it at that moment. We don't want to analyze my water bottle that's some amount of miles away. I don't know where this video was filmed, but it's not relevant. So we're not going to include it in the system because it doesn't matter. The amount of energy stored in my water bottle from this potential energy, it doesn't have any effect on what's going on over there. It's not part of the system. It's not what we care about. So why does the system matter? Why do we need to define the system? So the main reason why we want to define a system is because within a system, if there's no outside force acting on it, no external force, then we're going to say that energy is conserved. And that's huge. This idea of conservation of energy is how we can approach so many topics and so many problems in physics. So within a system, energy is going to be conserved. This idea is called the conservation of energy. This idea that the total energy within a system is conserved. The amount of energy you have when you start equals the amount of energy at any point in between, and then the energy when you finish. This is a huge law, and it's a huge idea where we can construct a lot of arguments from. So like in that paragraph length response, we have to say, hey, what physical laws are we using to answer our question? Conservation of energy is a great way to approach so many questions. So kind of the way the College Board defines energy or conservation of energy is saying that energy is neither created nor destroyed. If one form of energy in a system decreases, it must appear in an equal amount in another form. So that's just another way of saying conservation. So if it goes down at one point, if the potential energy goes down, the kinetic has to go up, just as an example. So we're saying within a system, energy can be transformed into energy of another kind. So we're saying, hey, like we can have the same amount of energy in our system. It may just be in different forms. It may be potential. It may be kinetic. So before we get too deep into energy and systems and all that good stuff, I just want to kind of remind us about the types of energy that we have, the types of energy that we may see, just before we get any deeper into energy conservation. So yeah, we're going to define the types of energy that we're dealing with, and I don't know, oh wait, no. Yeah, it's just going to be easier if we know what types of energy we're talking about before we discuss anything else. So one type of energy is going to be translational kinetic energy. When we talked about it before, we just called it kinetic energy because we weren't ready to address the fact that things were spinning and rotating. But now we're going to be a little bit more specific. Translational kinetic energy is going to be for things that are translating or moving. That root word or stem trans means across. I think it's like a Greek or Latin root word or stem word, I forget. We had to learn that all the time in high school, and I feel like you guys don't do that. I don't know, whatever. But so translational across, something that's moving, moving. So this translational kinetic energy is the energy of motion. And pretty much the way that we can identify if something has this translational kinetic energy is if it's moving. Is this object moving from one spot to another? If we look at the equation for translational kinetic energy is just going to be 1/2 mv squared, where the m stands for mass and the v stands for velocity, or speed, sorry, so speed. And the reason we're kind of calling it speed is because the direction that it's moving doesn't matter. If my pen here is moving to the right or to the left at the same speed, it still has the same amount of kinetic energy. So here I just have I don't know, this is what came to my mind when I thought of an object moving. I guess I just miss bowling. I don't bowl that much. I don't know why I said that. But so this ball, this man forces the ball, and it has kinetic energy. It has this motion and this ability to do something associated with it moving. And here's just a bigger version of that GIF. Alright, and then the next one, this is kind of our newest form of energy, the one that we talked about most recently, is a rotational kinetic energy. And it's an energy of motion, so we can think about it when objects are moving, but instead of objects moving or translating, so moving across something, it's going to be objects that are spinning. So this kinetic energy is the energy of rotational motion. If an object is spinning, it has this kinetic energy. So a little way to identify it is if our object is spinning, it has this rotational kinetic energy. And our equation for that, it looks just like our equation for translational kinetic energy, this idea that we have 1/2 I times omega squared, where I stands for that moment of inertia, and then that omega stands for the rotational velocity. And here's another example, just kind of for this, we see, oh, these windmill blades, these are spinning. So these are spinning because of the wind acting on them, and that's creating this usable form of energy. So it's in there then spinning some gear and then transferring that energy to electrical energy, but that's a type of energy. This rotational motion is a form of energy. Then we have our potential energy, so gravitational potential energy. This is a stored energy that's associated with an object's position in a gravitational field. That's kind of a fancy way of saying things, pretty much just saying, hey, if we lift something up to some height within a gravitational field like we have on Earth, then it has this energy. It has this potential to do something. It's not doing something at that moment, but it has the potential. It has the ability to do something. So the way that we can kind of indicate this one is if our object is at some height above what we're calling 0 meters, then it has this gravitational potential energy. So our equation for that is mg times delta y, where m is mass, g is the gravitational field strength. So if we're talking about Earth, we can call it 9.8. And then this delta y is the object's height difference above 0 meters. And the reason they call it delta y, this was confusing when we learned it the first time, is it's saying how different is it from some reference point? What's its height above something? If you just say, oh, well, this is at, I don't know, 1 meter, this pen that's sitting on the table, if you say, oh, it's at 1 meter, I know you can't see it, sorry. You say, oh, this is at 1 meter, then it doesn't mean anything. That could be like 0. It cares about how much does it change from your reference point. So if I say, oh, it's, I don't know, 0.4 meters above the table, that's where we start to care about it. Then we can say, oh, it has this potential energy. So we're referencing it to something. So to say, what's its height above something? And usually we'll just call our lowest point 0 meters, and then say, what's its height difference from 0 meters? Is it a meter above 0 meters, 2 meters? What's its height difference above some 0 position? So here's an example. Right now, this man, he has these weights, they're lifted up. This picture is really funny to me, and I don't know why. He's just like, he looks really bored. I don't know, something about it is just really funny. But so these weights are at some height above the floor, above 0, so they have this potential energy. If he dropped them, they have the ability to do something. Then the kind of final one. We have this elastic or spring potential energy. We can think about them with the same terminology, either elastic or spring, but it's this energy that's associated with a spring-like object's compression or stretch. So again, it's this stored energy, and it depends on how much we stretch or compress an object. So the indicator, the way we're going to look for this, is if we have some sort of object that's deformed. If it's either stretched or if it's compressed, or stretched or compressed, then we know that it's going to have this spring potential energy associated with it. If we have some sort of spring-like object, that'll reform its shape. If I took clay and I deformed it, it wouldn't spring back. But most objects, if you kind of deform them, they'll spring back to their initial position. So we have this equation is 1/2 kx squared, where k is our spring constant, and then x is just what distance are you compressing it or stretching it from its equilibrium position. So here's an example. I like this example because it's not like a spring, it's not as obvious. But if you're jumping on a diving board, this board, it physically bends, it physically compresses or stretches away from its equilibrium position, and it kind of gives this person some energy. They jump down on it, and then this energy is stored in the board, and it lets them get to a higher height than they would have if they just jumped. So everything that we just talked about, this is kind of a word that the College Board really likes using. I never remember learning about it back in my physics stuff, but College Board really likes talking about mechanical energy. So the total mechanical energy of the system is just the sum of the potential energy and the kinetic energy at some given point. So how much potential and kinetic energy do we have available? And the reason that they define this as something different as this mechanical energy is because these types of energy can do work on our system. So we call them this total mechanical energy. These types of energy can be productive. They can do something. We can transfer it and we can get it back. If we think about the other types of energy that we've talked about that aren't mechanical energy, so the ones that are not mechanical energy, like thermal energy, this energy associated with heat, if you rub your hands together, you know that they get warm. And yes, there's this energy associated with that warmth. There's this thermal energy, but we can't use that thermal energy. It's not usable. We can't come back to our hands and suck this energy back up and say, oh, I want to use that. Now this energy is potential energy. That wouldn't make any sense. We can't just turn that thermal energy back into something. So we differentiate it. We say that's not mechanical energy because we can't use it. It doesn't become this usable form of energy. Same with like chemical energy. There's energy associated with chemical bonds. We don't really use it too much in physics, but sometimes we use it as a cop-out. Like if a person does something, we say, oh, the person had chemical energy stored in their body, and they use that to lift up the pen or something like that. And again, this one, we can't turn it back. Like we can't take kinetic energy and turn it into chemical energy back into your body. Like we can't be like, okay, you're hungry, you used all your energy, go run around, you're going to get kinetic energy, and then you can transfer that back to chemical energy. That doesn't happen. That doesn't make any sense. So we don't call this a mechanical energy because we can't use it to, we can't like reverse it. We can't go from one form of energy back to chemical. Just like with thermal, we can't go from thermal back to something. So these mechanical types of energy, they can be transformed, they can go from one type to the other, we can use it, we can get it back. We differentiate these because we can't use them. They're not as usable. So far what we have is we have this idea that energy is conserved within a system. So energy can be transformed from one type to the other. It can be transformed from kinetic translational to kinetic rotational to gravitational potential to elastic potential to thermal energy. But so then now what we want to think about is how can we actually use these to solve problems? And the main way that we did this, our main setup for energy to help us think about what was going on, is through these LOL diagrams. So these LOL diagrams are tools that help us keep track of our energy. So what we have to do when we approach these LOL diagrams is, number one, first and foremost, is define our system. So think about what objects do we care about. Sometimes it'll tell you, sometimes it won't, and usually if it doesn't tell us, it'll be pretty obvious. Then we have to define the environment. So pretty much that's easy to do. Anything that's not part of our system is part of the environment. So yeah, anything that's not in our system is the environment. Then we're going to identify our first point of interest and see what kind of energy is. We'll run through our text. We said, hey, this is how we identify potential energy. This is how we identify kinetic rotational. This is how we identify kinetic translational. So we'll see what kinds of energy do we have. And then we'll find the second point of interest and say, hey, something changed. Something's different from this first point to the second point. What kind of energy do we have at the second point? And then we'll determine if any energy is lost to the environment or gained by the environment. So yeah, we'll do a few examples of this. So this is the first one that we saw when we first did our LOL diagrams. So take a quick minute and try to think about this. Don't feel like you have to draw it or write it out, but just take a quick second. Let's say the system consists of a spring, the cart, and the track, and the earth. So we have this cart over here. This is our first point. This is our second point. So our system is pretty much everything we're looking at: the spring, the cart, the track, and the earth. So if we're thinking about this at point A, think about what kind of energy we have, and then think about what kind of energy we have at point B. And let's say that it's frictionless. I didn't specify that, but let's say that it's frictionless. Take a quick second. All right, so at point A, let's go through our checks. At point A, we're not moving, we're not at some height above zero, but we do have a compressed spring. So we can say, oh, sorry, I'll kind of change this. So we can say, oh, well, we do have this spring potential energy. At point B, we're moving, and we're at some height above zero. So we have this gravitational potential energy, and we have this kinetic energy. So we have this transfer of energy from spring, or this transformation of energy from spring potential energy to kinetic plus gravitational potential energy. And everything that we're looking at here that could give our cart energy is in our system. So we don't have any energy flow outside the system. So we have this idea that the spring potential goes from kinetic, or goes to kinetic and gravitational. And then we can use our mathematical equations to solve if we're given numbers. And then one quick little thing is, we've been including Earth as part of our system, but why do we do that? Like, why does it matter that the Earth is part of our system? So take a quick second, think about that. It's a good question. It's a lot deeper than you think it would, but it's important to include the Earth in our system. Take a quick second. So the reason we do it is because that's kind of where our potential energy is coming from. Our potential energy is coming from the interaction with our object and the Earth. If we were out in space and there was no other objects around and we didn't have anything massive that was creating a gravitational field, if we put the cart at this location of B, it wouldn't fall down. It wouldn't go down, right? It wouldn't want to fall. It wouldn't want to do something while it was falling. If we pick up an object here on Earth, we say, okay, it's picked up, it has some sort of gravitational potential energy, and then when it falls, it can do something. Like I felt that in my hand. It has this ability to do something. If you were out in the middle of space and you picked up an object, it would just kind of float there in front of you. So it wouldn't want to fall and it wouldn't be able to do anything. So we include Earth as part of our system because the gravitational potential energy is really this interaction between the Earth and our object. So it's important that we include Earth in there because otherwise we wouldn't have a potential to do anything. So it's important to include the Earth as part of our system. All right, so now what we're going to look at is a quick real life example. If anybody's missing sports, honestly, this is a fun replacement. It's not a great replacement, but man, it's pretty fun. Honestly, it's a good old time. So this YouTube channel, it's called, let's see, what's the YouTube channel called? Okay, let me pause this really quick so we can actually get going. So this one's kind of a special, the YouTube channel is called Gels Marble Runs. Let's see, this thing is freaking out. Okay, there we go. So this is kind of a special one. Apparently they have this Formula One racer who's calling it. But so this is the trials. Usually there's a bunch of marbles. We'll see this in a second. A bunch of marbles competing with each other. This is just the trials, I think, to see what position they start in. But this person, he's been doing this for a while. He sets up these marble races them all, and then does a fantastic job with commentary. It's very funny. It's a really good way to spend some time. So this is just the qualifiers. But so we have different, yeah, we'll watch this really quick. But we kind of have, we start off at this high point, and then we go down the track, and we increase speed as we decrease our height. And this is freaking out. Yeah, so cool. So what I want to look at really quick is kind of thinking about making this LOL diagram for when it's at the top of the ramp and then when the marble's at the bottom of the ramp. So what kind of energy would we have if we think about our system being the marble, the Earth, and the track? And then one thing I also want you to think about really quickly is why would some marbles be faster than others? So just kind of think about those two things. What would this LOL diagram look like? And then why would some marbles be faster than others? So think about this for a hot second, and then we'll get to it. All right, so hopefully you thought about that. So what I'm thinking is at the very top, we just have this gravitational potential energy. These marbles are at some height. And then at the end of it, we have these marbles are moving. They have some sort of velocity associated with them. They have this kinetic energy. And then they have this thermal energy. Maybe throughout it, some of the heat, or there was collisions with the marble and the track. Maybe that sped it up. We have friction between the marble and the track, so that was kind of heating up the track. And because the track is a part of our system, we're going to call it thermal energy. We're going to say, hey, this energy is still contained in our system. It's contained in this thermal energy. It's not part of our mechanical energy. We can't use it, but it's still in our system as this thermal energy because the track is part of our system and the track is what's hot. So if we're looking at this, we can say, and I don't know if you can see this because I may be in the way. No, that's not. There we go. So with this, we can say, okay, we go from gravitational potential energy to the types of energy we have. We can say we have some kinetic translational because it's physically moving, it's translating. We have some rotational kinetic energy because this marble is spinning, so it's, it's rotating, so it's spinning. And then the thermal that we talked about. And then kind of an idea about why some would be faster than the others. Maybe it's based on the collisions. We know that when we have this collision, the track is going to heat up a little bit. There's going to be this impact. It's going to start to speed up the molecules in the track. They're going to get a little bit warm. We're going to have this thermal energy. So maybe some collisions take away some of that thermal energy, or maybe just based on the path. Maybe one is just covering less distance overall. It's able to be more direct. I don't know, but just kind of something fun to think about. Maybe it's this idea of thermal energy and how much energy is lost with each little collision that we have. So what we want to think about is what happens if energy leaves the system. So we've been talking about kind of contained systems. We talked about thermal energy being a part of our system because the track is part of our system. And we said that energy is conserved within a system if there's no external forces acting on it. So what we want to think about now is what happens if energy leaves the system? So we've defined work before when we talked about energy. Work is super important. Work is us saying work is what happens when we transfer energy to our system or from our system by applying some sort of external force on the system. So if we apply an external force, so some object from outside of our system, something external, something from the environment, forces our system, it is either doing work on our system or work is being done on that object. But either way, when that happens, the energy within our system is going to decrease. Now the total energy overall won't decrease. That energy is just going to leave our system. So yeah, so what it is, it's work is causing a change in the energy of our system. So overall, yes, energy is conserved, but some of the energy is gone within our system. So in order for energy to be transferred into or out of the system, we need an external force that can cause the object in the system to undergo a displacement. And we have this equation here for our change in energy or our work. We're saying the change in energy is equal to work is equal to force that's parallel to our distance or displacement equals FD cosine theta. So here's an example. Let's try this one out. So we're saying the system is going to be, or I'll show you the video, but the system is the marble, the track, and the earth, and not the motorized ramp. So this is kind of more normal for these videos, what they more so look like. We got a nice little ramp going. I think, yeah, they're doing 10 laps. And again, this guy, he just does an excellent job of just calling it and making it feel like real sports. He makes up like little names for all of the marbles. He's got this nice little interface that tells you when there's a lead change. It's very fun. But yeah, so they reach the bottom of the lap. And then there's this conveyor belt, kind of lifts them back up again. We'll see that in a second. Yeah, so they have this conveyor belt. It's made of those like connects things, I think, right? Is that what those are called? And then lifts them back up. All right, so if we're saying that the system is the marble, the track, and the earth, and not the motorized ramp, what does this look like from A to B? What kind of energy transformations do we have? So give it a quick second, think about it, and then we'll talk about it. All right, so at the beginning, our marble isn't moving. It's not at some height. There's no spring. So we really don't have any energy at the beginning. At the end, though, our marble is lifted up to some height. So it has this gravitational potential energy. And we want to think about where did that come from, because the ramp is not part of our system. So what we can say is work was done on our system. The ramp, the motorized ramp, supplied an external force on our object, and it did work on our system. It added energy to our system. Before we had no energy, and now we do. Now we have some amount of gravitational potential energy. So the ramp is doing work on our system. So we can say the work is equal to the amount of potential energy that our system changed by. And again, the energy overall in the whole entire universe is conserved. The energy from the ramp came from somewhere that was then transferred to the marble, which is then transferred back. So the overall energy in the universe is conserved. But within that system, we don't have a conservation. We have work done on the system. So work is done on our marble to add energy to our system. So then we kind of have this weird equation for work, this delta E equals W equals force parallel to displacement equals FD cosine theta. I just want to talk about that weirdness really quick. So this first part is kind of nice. It's saying, hey, work is equal to the change in energy of our system. So this idea that the amount of energy in our system changes when we do work on our system. So that's nice. This one's straightforward. This delta means change. So how much our energy changes is equal to our work. That one's nice. This next one is a little bit weird, but it's saying the force applied in the same direction as the displacement is the force that can cause work. So we're focusing on the force that is causing the displacement. If you push an object to the right, you're going to displace that object to the right. So we care about the force that's in the direction or the same axis as the displacement. Like if we pushed an object and then there was friction acting on it and it slowed down, we kind of have the object moving, just being displaced to the left in this case, the friction is acting to the right, but they're still parallel to each other. So the friction's working against it, but they're still parallel. That friction is causing the displacement to kind of change. And then the last part, that one's kind of the weirdest part, and it kind of just works in a few specific cases depending on how we define the angle. But if we're looking at this case where we say, okay, we have this box that's at rest, and then we force it at some angle, we can kind of split this force into two components. So we're forcing it, and our object starts to speed up. So the force that we care about here that changed the energy, right? It had no kinetic energy to having some kinetic energy. So the force that we care about is really this cosine piece. We care about just the cosine component of the force, this x component. If we think about the sine component, yeah, we had some force that was pulling it in this sine direction, or in this y direction, but when we look at it, all the kinetic energy is in this x direction. So it didn't gain any kinetic energy due to this upwards pull. It only gained kinetic energy due to this xwards, this rightwards pull. So we only care about that rightwards pull, the part that actually changed the energy. So we're saying, hey, this thing was displaced to the right, so we care about the force that's acting to the right. So that's just kind of a weird little situation that sometimes we have to think about. The full force doesn't matter because that y component doesn't matter. That y component didn't change the energy of our force, of our object in this case. So then a few quick little things. If we're looking at graphs, so kind of just general graphs of everything, one main thing that's pretty tricky is this idea that the area under a force versus displacement graph tells us the amount of work that is done on the system. So if we look here, we have a 5 Newton force that's sustained for 5 meters. So during that time, we have an increase of energy. We have work done. We have 25 joules of work done. So we're pushing in the positive direction, it's displaced in the positive direction, and 25 joules of work is done on our system. We've increased the amount of energy in our system by forcing it over that displacement. And then the weirdest part, this is where we can't use our equation anymore, right? Here our equation totally works. We did F times D, 5 times 5, 25. So that totally works. But when we have a changing force, then our equation doesn't work, so we have to rely on our graphs. So here we're saying the force is changing. It's still being displaced in the positive direction, so we still have positive work done on it. We still have work acting to increase the energy of our system. It's just kind of the amount that it's increasing is slowing down. It's decreasing over time. The amount that it's changing is decreasing. So here we can still figure out how much work we added. It's just we have to use our trig, or our geometry. Then kind of a part that we didn't talk about earlier, but we did a little bit. Sorry, I've done a lot of talking. I should edit this, but it takes forever to put in the editing system, so I don't do it. I'm sorry about that. So final little bit is when we're looking at energy graphs, sometimes it's going to ask you to graph the energy in a system versus displacement. The reason they do that is a little bit tricky. It's just because our spring potential energy is based on x squared, and they want to make sure you know what a y versus x squared graph looks like. So kind of a few tricks with that when they ask you about it. Unless there's an external force acting on the system, the total energy is going to be constant. So sometimes they'll say something like graph the total energy. So you'll just draw a line that says, hey, the amount of energy in our system is going to be the same throughout it. So really the main tricky part comes from if there's a spring or elastic item, remember that the amount of spring potential energy changes with the displacement squared. So it will change with displacement squared, and then the increased energy will be the inverse of this graph. So I have a picture of what I'm talking about here. It's a little bit confusing. Really quickly, we'll look at this PhET simulation. If it loads. So this one, it's not great, but it kind of helps us think about the energy, how it changes with x squared. If we squish it more, we have this nice curved line. We kind of have this energy versus displacement squared graph. We see it's kind of like this upwards facing parabola. So kind of to get a little bit deeper with that, if we have this situation like we have down here, where we're saying we have this box that's going to be propelled by a spring. So we're going to say, okay, this box is attached to this spring. It's going to start off at x equals 0, and then once it reaches the equilibrium position of the spring, the box will just keep on moving. The box will keep on moving with kinetic energy. So throughout this whole entire motion, if we're picturing the spring and the box and the earth and the track to be part of our system, then energy is going to be conserved the whole time. So if they asked us to graph the total energy throughout this object's displacement, we'll say, okay, the total energy is going to be constant. We're not going to be decreasing our total energy because we know that within our system, energy is conserved. Then if we're looking at this, our spring potential energy or our elastic potential energy, we have this situation where it's decreasing over time. We have this situation where at first it has a lot of stored energy, and then it's decreasing with displacement squared. So we kind of have this downwards facing parabola. Right? We see, okay, we start with the full amount, and then eventually it goes to 0 because eventually that spring will be at its equilibrium point. But it's going to decrease with x squared. It starts off with the most, and then we know that energy, spring potential energy, is related to 1/2 or equal to 1/2 kx squared, so it changes with the square of x. And then to compensate that, to make our total energy be equal, to make it be conserved, we have to kind of have the inverse of it as our other form of energy. So in this case, it's the kinetic energy. So we're saying, hey, as the spring potential energy decreases, our kinetic energy has to increase by the inverse amount because we have to make sure that at every point our total is the same. So if we look at this starting point, we have 2 plus 0 equals 2. If we look over here, we have 1 plus 1, it's still equal to 2. We still have the same amount of energy. And this happens at every single case. We have to make sure that the total energy in our graph still equals the total energy in our system. Then the final little thing, saying power is just the rate of transformation of energy. So a rate is just when something is happening over time. So our power is just going to be our change in energy over our change in time. They don't ask too much about power, but pretty much the main idea is if our energy changes a lot in a short amount of time, that's a lot of power. If it takes you a day to lift something, you're not very powerful. But if it takes you a quick little bit of seconds, then you got some power to you. So what I want us to do is kind of the last final things. And I'll put this in the Google form. But we have this Rube Goldberg machine from earlier. What I want you to do is just kind of identify 2 moments where energy transfer occurs and then describe what is happening and what is happening with the energy transfer. So just as a little example, in the first little bit, we can say at 2 seconds, the toilet paper roll is not moving and has some potential energy because it's at a height above the surface. The hand does work on the toilet paper roll, giving it a small amount of kinetic energy. As it rolls down the ramp, the potential energy turns into kinetic energy. The energy is then transferred to the next toilet paper roll. So that's just kind of this very first part where they tap it. At first it has no energy, then push it over some small displacement, gets it rolling, and yeah, it kind of gains this kinetic energy, both translational and rotational. And then the final thing is I have some practice questions for you.